who is going to talk about probing high-dimensional spaces with AI, from theory design to parameter interference in particle physics. Ashik did his PhD from Sakle, and then postdocs at UC Irvine and Caltech. No, Berkeley. Right.
Yeah.
Yes, Berkeley. Yes. Okay. Right. And today he's going to talk about AI, and okay, this is a hot topic these days. So, over to you, Ashik. Yes.
Thank you very much, and I just wanted to thank you for having me here. It's been really nice. It's my first time at IISc, and I'm really enjoying it, chatting with all of you here. And indeed, I'm excited to talk to you about this broad thing of high-dimensional spaces, and I hope I will show you how traditionally we haven't really been able to deal with high-dimensional problems, because of which we make certain simplifications and try to deal with them in bite-sized pieces. And AI allows us to remove all of these simplification assumptions and really explore the high-dimensional space in its entirety, right? And so, as physicists, at least fundamental physics researchers, what is your core job? On the one hand, you want to design theories that somehow explain the universe as we see it, and make predictions that we can then go and test in experiments, right? And it's not just a one-way street. You design a theory, you build an experiment, but sometimes you get data from an experiment, and then you realize you need to update your theory in a way that accommodates what you actually see in nature. And so overall, I would say the main goals of our field are theory design, experiment design, and then statistics. So to make the most of the data we're generating in these gigantic experiments. And today I'll talk about two of these three aspects. All right, so let's start with, I'm going to start with theory design, which is a fun project that we've worked on over the last couple of years. And it's a direction that we are going to invest in a lot. So half of my research group is going to be working on this direction in the future. And then I'll talk about some experiment stuff where we have gone a lot further and done rigorous and meticulous uncertainty quantification and so on. So you'll see two aspects of the process, coming up with new directions and also really taking them to the end. All right, so when we build physicists, we build mathematical models. Of course, all models are wrong and some are useful. So what is a useful model? It is very subjective, but at least in my opinion, something that I find interesting is if the model is somehow predictive. What would that be? An example, of course, is the best example is general relativity, which not only boils down to Newtonian gravity in the right limits, but also gives you new predictions, like it tells you about the perihelion of Mercury, but also makes completely new predictions, things like black holes or gravitational waves that we didn't even manage to discover until many decades afterwards. Of course, particle theories are a little bit more complicated and messy. There's a lot more back and forth between data and coming back and improving your theory. But nonetheless, we have come very, very far. In fact, these four cute little lines describe everything that you can see and taste and feel in the whole universe, right? If you expand it out, it gets a bit hairy, but nonetheless, this theory is very, very predictive. So it predicts a whole bunch of, once you fit certain parameters, it can predict a whole bunch of other things, and then you can go into an experiment and try to do measurements. And so we find that the data and the theory seem to be very compatible within the uncertainties. You can start to get more ambitious, make more precise and more complicated measurements, but each time till now we found that standard model wins, and every other beyond standard model theory seems to not do as well as the standard model. This doesn't mean that the story is over. We know that it's a deeply flawed model. We know, first of all, that it can't explain 85% of all the matter in the universe, which we just call dark matter. There are many other problems, matter, antimatter, asymmetry, and so on. The one I want to focus on is the fact that the standard model doesn't predict any mass for the neutrinos. And of course, we've seen that there are three kinds of neutrinos, and they oscillate between one another, and that implies that there should be some kind of a mass. Yeah, so the question might be, like, how can we come up with models that can explain this stuff very well? Of course, there are many ways. People have come up with many models that are interesting, but it's also an interesting place that you can explore some kind of more automated methods for designing of theories, right? So how would you design your first particle physics model? You might say make some, first of all, I want to motivate why it's interesting to explore things more systematically. It's basically because the space of mathematical tricks that are available to us is truly ginormous. If you think of the old electroweak theory, it could explain a whole bunch of things, but it couldn't give mass to things like Z bosons and the W bosons, because any way we try to give them mass, it seems to violate some symmetry or the other, right? And of course, this was solved by the Higgs mechanism. But if you ask me, it seems, the Higgs mechanism to me at least seems kind of unintuitive. I wouldn't have been able to come up with it on my own. And it was in fact inspired by research from superconductivity, right? So these folks realized that if you introduce a scalar field, it changes the behavior of these other fields and makes long-range interactions into short-range interactions. And we realized that we can pick that idea up, put it into particle physics, and voila, Z and W suddenly have a mass, right? And so the question I wonder is, what if the superconductivity people hadn't stumbled upon this mechanism? Would we have come up with it on our own? Probably, but it might have taken a bit longer. And the other question is, could the solutions to current open problems also be in these weird, unintuitive mathematical tricks that nobody has tried to has attempted to use until now, right? And so that's the context in which we want to try to explore neutrino model building, try to explain the masses, and remember the main point here is not to build a new neutrino model. A whole bunch of people have done that before. It's really a testing ground to come up with these methods for automatic theory design. All right, so how would you design your first model? You will make some choices of fields and symmetries. Choosing fields is kind of like choosing what kind of particles populate your universe. You can choose a whole bunch of different fields. In fact, if you choose hundreds of fields, you will have so many free parameters that you will fit any amount of data in front of you. So you'll be very compatible with data, but nobody's going to take your theory seriously. If you add symmetries, you say that certain fields can only transform in certain ways, and it adds richness into your model. It gives the model this kind of internal structure and understanding of the universe, and it adds restrictions. So it reduces the number of free parameters. So this is a nice way you can add fields and then also add symmetries to bring down the flexibility of the model. And you usually will talk about symmetries in terms of symmetry groups, and you put the fields in certain representations of these groups. SU2 is a common one. SU3 is also another common one that's used in the standard model, but there's so many different groups we could be playing with. We like to put them in these geometric little shapes and pretend that we understand what's going on, but really there are too many mathematical groups, and I'm confident there's nobody who has intuition for all of them. And this is what makes it risky to try a completely new group, because you might spend a couple of months figuring out how this group behaves, and in the end realize that this was a dead end. There's no way I can build a nice neutrino model using a particular new group. And that's why if you look at all the typical models that come out, they use the same few groups again and again, because why would you make this very risky investment of time? And that's where an automated algorithm would lower that risk to try new ideas and see what is actually interesting. Right? In fact, I like to joke that theory model building sometimes it looks like an artisanal craft, where you've kind of fallen in love with a certain kind of symmetry. It makes a lot of intuitive sense to you, and so you want to build a model using this group. But then there are a vast majority of groups that remain unloved and therefore underexplored. And that seems a bit unfair. So what if we can build a more industrial, systematic way of exploring all of these different groups? To do that, I need to come up with some kind of a pipeline, right? So I want to make some choice of fields and symmetries, but then I need to somehow automatically calculate the Lagrangian, which I can do with some math software, which we plugged in here. From the Lagrangian, we have encoded all the rules of the universe, right? So we can then make predictions of what would happen in individual experiments, compare that to actual experiments using statistics software, and finally evaluate the quality of your model. This is not just the fit to data, but also somehow evaluation of your elegance, for example, number of free parameters, fine tuning, and so on. And if you were to randomly make a choice of fields and symmetries and do this whole thing, chances are you wouldn't do very well, because the space of models you could build is ginormous and the fraction that is actually interesting is tiny, right? And this is where AI is going to come in to search this space more intelligently. And remember that what, at least in this setup, what we care about is models that explain data well, so good fits with few free parameters. So we have this AI agent over here. It is able to interact with math and physics software. So it makes some choices of fields and symmetries and then asks Pi discrete, which is the math software, to calculate the Lagrangian for us. It can then interact with the physics software to make predictions, and then the statistics software to fit free parameters and compare with data. Right? And once you have the results, you can construct some kind of a reward function, including all of these metrics of performance, and then give it back to the agent. And eventually you want the agent to, over iterations, learn how to automatically build these models. Right? So that's at least the idea, and we tested it out. It turns out it does work. In fact, it generates maybe even too many models. So let's see what's going on. Here we're looking at how the agent performs as a function of time. Right? And we can see the compatibility, the chi-square, goes down, which means the compatibility gets better as the agent explores more and more and more. So that's good. But one easy way to do that would be to just build models with bigger and bigger free parameters. But that's not what happens. In the orange, we can see that it learns also to reduce the number of free parameters at the same time as it's reducing the chi-square distance. Right? So that means it's doing something intelligent. And we can look at the fraction of good models that it generates over its exploration, and it seems to find more and more frequently good models. What is good models? We define it as the space. So right now it's searching through the space of A4, Z4 symmetries. Right? This is the most typical symmetry group that you would use to build such models. And we define good models as having 7 or fewer parameters and 10 or fewer smaller in chi-square. Right? And we can see that there is the search does populate this space a little bit. In fact, you can inspect individual models and convince yourself that we recover the same structure as all the models that people have written down by hand and published over the last 20 years. And this is not surprising, right? So we can, the very least your agent should be able to do is reproduce the results you've already got from historical searches. Right, so that's good. That means it's doing something. It's not totally a dumb idea. And so we want to do some take it further now. So instead of Z4, we give it the flexibility. Oh, by the way, the more bottom and to the left, the better the model is, of course. And so now instead of Z4, we let it choose what kind of group it wants to have between I think 0 and 7. All right. And so what happens now, we see that again, learning seems to be doing something. It's less clear if it's going in the right direction until you look at the fraction of good models. That does go up. And in fact, in the 2D plot, we can see that now the fraction of models that are good, which means a few parameters and good chi-square, is actually even better populated than before. What that tells us is that when we give the agent more flexibility to make more choices, it's able to find different ways of designing models that fit our criteria. Right? So now it's starting to get interesting. But A4ZN is still a space people have looked at before. But we want to, at this point, maybe look at an individual model and convince ourselves that things are looking all right. So this is an example model that the agent finds. So here is the groups it chooses, so Z7, and then the fields that exist in this universe. So there's a Higgs doublet. This is not really a choice. We've restricted the space of the search to supersymmetric theories, so this comes in quite naturally. But the agent does make a choice of 3 flavons. These are 3 new particles that the theory predicts. It could have made more particles, fewer particles. It chose 3 in this instance. And you have the right-handed neutrinos, leptons, singlets, and of course the doublets. Right? This is quite nice. And you can see the representations it's assigned to each of these fields and charges. Now, I am very new to neutrino model building, so this is all new to me, but we do have a student in the team, Victoria. She is a career neutrino model builder, and we asked her if we had locked you up in a room and given you these 2 groups and told you to build a model out of them, what would you build? And she said, yeah, I would probably build something very similar to this. So So these models don't seem out of the ordinary. They, if a human had to like invest a few hours, they would probably come up with something similar. Okay, so everything seems to be working fine, and so now it's time to try something new. This is a T19 symmetry, never before been tried for neutrino model building. Why? Because it just takes a lot of time to invest into a new symmetry, but there is a natural reason to try this. Is the smallest next symmetry group that you could have tried, and so wouldn't it be nice if we just let the agent run overnight, and in the morning we had an idea for whether this is a good, if it's worth investing any time in or not. And that's what we do. And so we woke up in the morning and we saw that this plot seems to be going up, so it's finding something. And then we looked at this plot, and we see that the good model range is quite nicely populated. So this is nice, and this is not necessarily going to be the case. It could have been that the T19 is just a useless symmetry, but we worked out for us. And because it's so well populated, it gives me the sense that there seems to be a rich landscape of viable neutrino theories that we had never previously studied that can be now built using T19. But that's a tall claim, right? We are looking at these statistical distributions. What are the models genuinely unique, or are they just like the same model with a new mustache, a new hat, and suddenly I'm convinced that it's a different model? To figure that out is not easy, but we can look at a few diagnostics. For example, we can look at how many effective number of new particles each theory is predicting, so the number of flavons. We can see that some theories predict only one new particle, some predict 6, and so there's this whole range, which means, okay, at least not all the models are the same, right? They make actually meaningfully different predictions. They also use different vacuum expectation values to cancel certain things out, so we can see that these models are also reasonably unique. And the most important thing to look at is how each field is put in a representation of a symmetry group. And we can see that they don't just, the agent doesn't just put the field in the same group every time. It's able to build models by putting, let's say, these doublets in different representations, right? So this doesn't tell me that all the hundreds of models I'm finding are all unique, but it does tell me that I am not just reproducing the same thing again and again. And then you can do more high-level checks of whether things are equivalent or not. Okay, but what this tells me is that T19 is genuinely interesting, and so when we're thinking about neutrino model building in the future, it might be interesting in addition to the usual symmetries to also consider T19. We can also look at the flexibility and fine-tuning and things like that for individual models, of course, and I'm showing you the example of one of the simplest models we had with only 4 free parameters because it's easy to visualize. And so we're looking at each of these free parameters, and as we change the best fit value, change the parameter from its best fit, we see how the chi-square blows up. Right, for some of them it doesn't blow up, it's quite smooth. What you don't notice here is that these two are quite fine-tuned. If you were to be able to read these numbers, you would see that it is at the 3rd decimal order, right? So this is not ideal, and so the idea would be in the future to add these kind of diagnostic plots also in the training loop, so that the agent knows that it's not just building a model that fits the data, but it's kind of fine-tuned, so maybe it can try to find something else instead. So yes, you mean the vacuum expectation? No. Vacuum alignment. We don't look at that yet because we haven't optimized that. Yes. Absolutely. It's definitely on our plan to do next. We haven't optimized it yet. We might have to do a separate search to put that into the loop. Yeah, but that's absolutely in the plans. Yeah, thank you. Yeah, there's not actually a very, so if you look at like literature, they will say like another group that we might look at in the future is T19 is the next smallest group that you could explore. So that's about it, that's the motivation. We could have tried 10 other groups and maybe one of them would work or something. But that's also something we want to do. We want to like explore like 100 new groups. Maybe not for this problem, but like in general, that's an interesting thing to have in your toolkit. But for that, you need to have everything about the group. You need the group and all of its irreducible representations, and that's a list we haven't compiled yet. Okay. So I showed you something fun, hopefully, about model building. Now we will switch gears completely and look at experiment. All right. So remember earlier we were designing new models. Each model has different free parameters that you need to fit and so on. Now we're going into a very specific regime where there's this one, we're working within one model, and we're trying to measure one parameter. So we're trying to measure essentially the width of the Higgs, which has a lot of implications about new physics, right? But it's just one parameter that has to be measured, and we want to see how well we can measure it. Right? And of course, in experiment, unlike in theory, machine learning has had a huge influence over the last 15 years. If you're doing simulation, detector simulation, you're probably doing it with machine learning. If you're doing reconstruction, you're definitely doing it with machine learning at this point. And of course, signal versus background separation has been done with machine learning for a very long time. But the final statistical inference, the measurement, the confidence interval, these kind of things are still done using the same old statistical techniques. In fact, if you had a grad student who joined your group now, you would hand them a book like this or like this, which were probably published before they were born. And by the time they've read the book cover to cover, they know the state-of-the-art method of doing statistical inference, right? And the question is it now time to also maybe modernize the statistical inference tools? To answer that, first, let's recall what is the standard way that we do measurements, at least in collider physics and often in other particle physics experiments. By now, our experiments are very, very complicated. You have detectors that have about 100 million independent sensors, which means if you look at the raw image of a collision, the image is 100 million dimensional, right? And nobody's trying to calculate probabilities of seeing these events in such high dimensions. Instead, hundreds of physicists come together to design clever algorithms to summarize this gigantic image into just one summary number. You have thousands of such collisions. Each of them becomes one number, and then you plug that into a histogram, right? And it's at this level that we do know how to do statistical inference. This is quite a big summary. So what might this look like? You might have a background only histogram that predicts what data should look like if you only had backgrounds, and you might have a signal model on top, and you compare it to data where of course you have no labels. And you might measure something called the signal strength, which will typically just enhance the overall normalization of your signal, right? This is the most typical measurement at the LHC. And so the name of the game is to calculate the likelihood. So you say, given this data, I kind of superimpose it onto this and say, what is the best fit? So what is the hypothesis that mu is equal to, or what is the likelihood of this hypothesis, mu is equal to 1 versus mu equals 2 versus mu equals 3, 4, 5, and so on, right, as the normalization goes up. And this is at the core of frequentist hypothesis tests, where you want to compare the likelihood of one hypothesis given the data versus another hypothesis, a reference, for the same data. And numerically, that is simply the probability of you having observed this data set if your hypothesis were to be true, right? You can flip things around. Okay, and this very nice lemma, statistics lemma from 100 years ago, called the Neyman-Pearson lemma, tells us that in fact, if you compute this quantity, and you take the ratio, that is the theoretical upper limit of the information you can get from the data. So this is the optimal test statistic to compare any two hypotheses. In reality, we do something slightly different. We don't just compare two hypotheses, we're comparing infinite hypotheses, because we have mu equals 0, 0.1, 0.2, all the way. And so we can compute the ratio and we take a log, so it's a log likelihood ratio. And we take it as a function of the mu, and then that's how we build, do a measurement and build a confidence interval. So the minimum here gives you your best fit value, maximum likelihood estimate. And then you somehow construct this kind of a belt that tells you how to build your 2 sigma confidence intervals. And so you say that everything that when the purple intersects the black, that is your one limit, and on the other side is the other limit, right? So when you report a result in your paper, you say the mass of the Higgs is such and such, plus minus this is what you're reporting. And how do you build this thing? You have to throw a whole bunch of toys or make certain assumptions to tell you that roughly, if you want a 2 sigma, then this you make a line around 4. Okay, this is generally how we do the measurements. But there is a bit of a challenge in certain analyses that we are trying to do now at the Large Hadron Collider, and these have quantum interference effects. So remember I told you that traditionally the signal strength only enhances the overall normalization of the signal, but things can be more complicated, especially for the Higgs width measurement. So this is done in the Higgs to 4 leptons channel. All right, so 4 leptons like 4 electrons, and you can look at the mass of these 4 leptons and the distribution of this. So in blue is the background only distribution, as if there was no Higgs, and then in pink is the background plus signal. Does this look strange? To those of you who are used to LHC plots, you will be surprised that the background only seems to have a higher cross section than the background plus signal, right? And that happens because of destructive quantum interference between these two processes. So by adding a second process, you're not increasing the probability, in fact you're decreasing the probability. That's a funny thing that happens with quantum interference, and in fact it doesn't just change the overall cross section, it changes the whole kinematic distributions in this high dimensional space in non-linear ways, where the dependence on mu becomes non-linear. Okay, and the point here is that in these cases, this summary that we're talking about of taking this image and compressing it into one number, that just does not work very well. I'm going to give you some intuitive explanation rather than math for why that is. So imagine that your real data lived in 2 dimensions, all right? So your first hypothesis predicts a large concentration of events here, and the second hypothesis, large concentration there. But for some reason, you can't do 2-dimensional analysis, so you need to summarize this. What would you do? You would maybe read off the x-axis and get this 1D projection. Right here too, you have good separation power between the blue and the red distribution, right? So the summary seems pretty nice. But what if I introduced a third hypothesis here, or a fourth one over there? Now suddenly, in the high dimensional space, I can still separate all of them very well, but in the 1D projection, I start to see these false degeneracies show up, right? And this is an intuitive explanation for what is actually happening for the most important measurements in collider physics, whether it's the Higgs width measurement, the Higgs self-coupling measurement, or in fact any measurement once you introduce systematic uncertainties, which is all measurements. And it is critically the case for effective field theory measurements. Okay, so sounds like all the important things we want to measure now are affected by these problems of summarizing, so we should just go to high dimensions, right? But building high dimensional histograms is a challenge. Imagine building a 1D histogram, you have only 6 bins. How many simulated samples do you need to plug into this histogram before you get a good idea for this probability distribution that it's estimating? Remember, histograms are ultimately giving you some estimate of a probability density. Right, so maybe 50 to 100 will give you enough samples to get a good idea for this, this density, right? Now what about a 2D histogram? 6 bins on the x-axis, but also 6 bins on the y-axis, so 36 bins overall. Now you need a lot more samples. Now think of a 50-dimensional histogram, 6 to the power 50 bins. How many samples do you need now? I can guarantee you that there's no experiment in the world that has enough samples to populate such a histogram, let alone going to millions of dimensions as you would need to really scale. So this is the curse of dimensionality, and this is why histograms do not scale to high dimensions very well. And so we need to find a new way to do density estimation in high dimensions, and that is where neural networks come into the game. Right, so neural networks are famously very good at handling high dimensional problems. And so the idea is, traditionally we would take high dimensional data, summarize it into a tiny histogram, and give that histogram to your statistical fit. You also tell the fit what hypothesis it is you want to test, mu equals 1 maybe, and the fit runs for a while, and then gives you some likelihood. Right, I want to drop that summary and take the high dimensional data and instead give it to a neural network. The rest of the story stays the same. I also tell the network what hypothesis it is I want to test, mu equals 1, and then the network directly should give me the likelihood ratio with respect to some reference. That's the idea. And these networks could be trained on simulations and applied on data. This is why this whole paradigm is often called neural simulation based inference. Right? And of course you're wondering, wait, but my simulations aren't very good. How am I going to deal with these uncertainties? Yeah, and we'll have to deal with that. And in fact, this is the reason these ideas for example, first were put out by this paper by Kyle Kramer and all in, I think, 2014, but nobody's actually used it in an experiment for a very long time, precisely for these reasons. There are so many open problems. Robustness, are you really going to trust a neural network to give you a likelihood? What if it's mismodeling something in a very tiny space? How are you going to propagate your systematic uncertainties through this network? How are you going to ensure your confidence intervals, which are done through this Neyman construction step? All of these were open problems, and this is why nobody actually tried to use this for real. And this is what we solved over about 4 years in the Atlas experiment. And that led to this big publication in Reports on Progress in Physics. Right, and we didn't just stop there. We took the method and applied it on actual data, and this gave us a new measurement of the Higgs width on the same run to data. So there was a previous publication from 2023 on this data using histograms, and we just completely blew that out of the water using a new technique. So we're going to see how that was done. Here's the big picture. We still are going to use networks to learn likelihood ratios, but instead of just using one network to do the whole job for us, we're going to break up the task into smaller pieces and have an individual network for each of them. And turns out that we can inject physics knowledge into the system. So we know how each of the pieces connects to the other. There's a known analytical physics formula that we get from our theoretical, from theory. And so we can plug those in, and that really improves the robustness of the technique. You'll see a little bit more in the next slide. But then we have additional neural networks, one per source of systematic uncertainty. So for example, a jet energy uncertainty or some other uncertainty, and they will change the final likelihood ratio to account for their respective sources of uncertainty. All right, and we can factorize these things out. And in fact, each of these boxes is not just one network, but an ensemble of 1,000 networks. And that lets us estimate the uncertainty of the fact that the network is not accurate. Right? So the uncertainty of the neural network training itself can be estimated using these ensembles. The whole thing requires, it's so we did it. So the way we train it is in the ensemble of 1,000. What we're trying to estimate is the uncertainty coming from the fact that we don't have an infinite training sample. Like if you had infinite data, then okay, all of these converge to this, the true probability. But because you have a finite training set, you don't. And so what we do is we bootstrap, and so each network gets a bootstrap version of the original data set. And I can show you later on in the plots that, so if you take each network and make a prediction on the same event, they give you a slightly different prediction, and you can use that that width as an uncertainty, and you can interpret it in a fully frequentist way. And then the propagation is even more tricky, because you are estimating these uncertainties on the different networks, but the impact is correlated. So you need to now take into account the correlation between the different networks, which we are able to do with another method called spurious signal method. And then so you see how each of these uncertainties impacts the final maximum likelihood estimate. And once you've done that on simulations, you can apply the same thing on data. It's tricky, and in fact this is the trickiest part of this method, and which is why we need to train 10,000 neural networks to estimate these kind of uncertainties. And once we put this paper out, there were a couple of theorists at MIT who came up with a better method. So I'll mention that as well. That reduces the complexity and actually improves the robustness. So there's a theoretical guarantee now that the uncertainty can be interpreted as a 2 sigma uncertainty, which we didn't have here. So it's quite nice. Okay, so this is the idea for how we make things work. So let's try to see why I'm trying to factorize the problem out into multiple networks. Right? See, in principle, I could use one network to train for one hypothesis mu versus a reference, and then as I change mu, I might need another network, or I might use the same network to learn the conditional probability. Right? But that means for every mu, I have to now go back and validate that my network probabilities are correct. This is an infinitely hard problem. Instead, I can notice that whatever hypothesis I am testing, it has contributions from the same 3 or 4 or 5 Feynman diagram. They have the same processes. One of them, let's say, is 2 gluons going to 2 Zs without any Higgs in the middle. The other one has this Higgs propagator in the middle, and so I know if I change the Higgs couplings, then it will change the probability. Right? So this has a linear, this has no dependence on Higgs couplings. This has a linear dependence on Higgs couplings. This interference term happens to have a square root dependence. These are all things I just know once I look at the Feynman diagram. Right? So I don't need the network to learn these things, and I only need the network to learn green versus gray, blue versus gray, and purple versus gray, and then I can plug back in this formula how each of these probabilities gets enhanced by the coupling. And this is how I'm able to inject physics knowledge and only need now 3 kinds of networks to estimate the full probability in this infinite space of mu's. Right? Because the interpolation, you notice, is only happening by the analytical formula. The networks are only estimating individual densities. Right? So this is the trick we use, and we use it again and again to factorize various different pieces and inject physics knowledge to make the whole method more robust. Okay, so this is all well and good, sounds plausible, but how do we validate and make sure that the method actually works? So there's a whole list of validation techniques that we designed also to just check if everything works, and I'm going to show you a couple of examples. One is for reweighting. So as it turns out, if you want to reweight 2 high-dimensional distributions, let's say this green and the blue are high-dimensional, the way to reweight them actually uses the likelihood ratio. So if you want to take events here, you'll have to give them weights smaller than 1, and that weight is determined by the likelihood ratio of an event in this part of the phase space. And I claim I have estimated likelihood ratios with neural networks. So here's where it connects. Turns out, if I believe I've already estimated this quantity, I can do this reweighting and then visually check if the reweighting works. If it works, that means the likelihood ratio is well estimated. But if I find any place where the 2 don't match, that means over there my likelihood ratio must be mismodeled. Alright, so this is one way to visually check what the network is learning. And so what we want to see is, so this is before reweighting the source, and after reweighting it should try to look like the green one. So if everything works well, we hope that the green and the orange will sit on top of one another, and that's what we see to a large extent. There are some fluctuations in the tails, and then you have to convince yourself whether these fluctuations are good enough or not. We look at lots of such plots. You also want to do high-level closure. For example, these are variables that the network has seen in training, so of course it does well. But what if you had some very complicated correlation between them? Would the reweighting also work there? And we see that you can use a matrix element-based observable, and which is one of the highest level observables you can think about. And after reweighting, the orange and the green sits right on top of one another. Alright, so these are all 1D marginals to try to convince yourself that this high-dimensional probability is being correctly estimated. But of course, you can also do high-dimensional goodness of fit tests, for example, with other machine learning techniques, and convince yourself that the fit is pretty good. So the probability that's being estimated reflects the true probability. Okay, this is one thing. None of these are like conclusive proofs. They're all indications that things are working. Another obvious thing you want to test is just run the whole neural network analysis on simulations at different true values of the parameter. In your simulations, I know that the true value is either 0.1 or 0.5 and so on. And I want to make sure that when I run the whole thing, that the maximum likelihood comes back exactly at the true point. And this is what I see, so that I can convince myself, okay, at least I don't see any obvious biases. There are many other diagnostics I could talk to you about. They're all in the backup slides if you want to look at them later. And of course, data versus MC comparisons to make sure that the simulations reflect reality. Okay, but then there's questions of all of this, systematics and confidence intervals. And this is a whole bunch of math that we do to solve this, but the core idea is that you take the same techniques that you would for uncertainty quantification in a histogram analysis and just extend it to a per event analysis. So you pretend that each bin in a histogram goes to infinitely small, and that allows you to extend the whole thing to these kind of high dimensional methods, right? And with that, I will jump straight to the final results that where we convinced ourselves that we can actually apply this on real data. So this took me 6 years, so it was very exciting when I finally saw results on real data. There's a lot going on. So the way to interpret these kind of plots is the narrower the curve is, the more precise your measurement is, all right? And we're going to focus on the 2 black lines. The black dashed line, this one, right? This is the histogram analysis, also which we worked on in Atlas for many years, optimized it as much as we could, and we published this in 2023. Then, exactly the same data, same simulation, just a new technique, and we get this solid line over here. So this is the level of improvement in our ability to reject the null hypothesis, which is what is required to discover this process. This needs to go all the way up. For 5 sigma, it needs to go up to 25. We're not there yet, but we've made a huge jump in the right direction, which is to discover this process. Right? And those of you in collider physics know that like 10% improvement is great, so this is like a 260% improvement. Right? And if you want to look at systematic uncertainties, this is the sensitivity if you didn't incorporate systematics, and this is the sensitivity it goes down once you incorporate systematic uncertainties. Of course, sensitivity goes down once you incorporate these kind of things, but it doesn't just wash away all the sensitivity. In fact, we are able to set two-sided limits for the very first time on the Higgs width using this kind of data. It was never possible before. We hadn't imagined that it would be possible. So this was a really satisfying moment for the entire analysis team when we were able to set a lower limit. Alright, so having seen all of this and made such a dent in an important Higgs measurement, it was time to take a step back and see how the field has progressed. There was a time in the 30s where you could look at a single event, look at this bendy trajectory and convince yourself that I must have discovered the positron. Right? But by the 90s, we had to get much more sophisticated and make statistical statements. My background only hypothesis predicts 7 events, but I see 27. And therefore, I can reject the background only hypothesis with a large confidence in favor of the top quark hypothesis. Right? And then by the 2010s, we became even more sophisticated, not just making statistical statements, but taking into account the shape information, although only in one dimension and in bins of a histogram, which is quite, it's summarizing information. And today we've taken the next logical step in this direction, taking into account the full high dimensional shape information in a continuous way without having to bin anything. And that is what you can do with neural inference. So this was quite exciting. These couple of papers came out last year. And since then, we've seen an explosion of interest in the method. So as I mentioned, there's this new paper. So theorists are now interested in quantifying statistical uncertainties in experiments, which is just, for me, really fun to see. So there's Jesse Thaler and his student who came up with a nicer way to quantify these neural network uncertainties that we were talking about. Do we want to plug that in? Anyway, I will proceed. So now there's also LHCb, which is a different experiment, and they have B-physics problems that I don't understand very well, but there's the student Jamie Gooding who is now bringing these kind of ideas into the LHCb experiment and incorporating it into the standard RUFIT package, which is a statistics package used across experiments. So suddenly these methods will be accessible to a larger community. Iris Hep is also designing these kind of fitting frameworks, and I know that the LZ experiment, which is a completely different dark matter experiment, very different from colliders, is exploring these kind of NSBI techniques. At the national labs, we are, in the US, we are now designing an automated workflow. So remember, this method might be powerful, but it's very, very, very expensive, right? 10,000 neural networks. And the student who worked on this, Jay Sandesera, he had to really babysit thousands of jobs. It's a really painful process. So we want to automate the whole thing. And that's what we do in this workflow, where you just give it the data set, and it'll automatically train 10,000 networks, do all these diagnostics to make sure the probabilities are correctly estimated, do these uncertainty quantifications. By the way, this is what I was telling you about. Each network in the ensemble gives a slightly different prediction of an event, and this width can be quantified as an uncertainty. Right? And so we then put this whole thing in a loop, and we optimize the network parameters until the uncertainties are small and the diagnostics are good. So this will save a student working for 2 years just babysitting jobs, and will also make these kind of AI supercomputers more accessible across experiments. But it's not just us physicists who are excited about neural inference. Turns out that this Ars Technica, which is a tech news website, it's pretty popular, They covered this work because they found it very interesting how AI is helping us handle quantum interference effects at the LHC in a way that was not possible before. So it's really fun to see the external community finding these things interesting. Okay, how am I doing on time? Yeah. Great. Okay. Okay, yeah. So the question is, will this help with BSM physics? The answer is, I mean, yes, but not. So if we have missed some signals, if we have not even thought about those signals, we will not find them with this. Because this is maximally model dependent. This is the most model dependent thing you can do, because I'm saying this in my simulation, this is what the signal looks like. I want you to go and find the signal. So the other angle is anomaly detection, which also uses similar machine learning techniques, but it doesn't assume a signal model. And those can be used to find BSM physics. The trade-off is these methods they cannot be beaten in what they do, which is to find the signal, if you know the signal. But if you're doing anomaly detection methods, they will be not as powerful as this, but they will be more broad. Yeah, if you know the signal, this basically does the best thing you can do. It just sucks up all the information from the simulation, gives you the right uncertainties, sucks up all the information from the data. The best you can do with an asterisk, and I will explain the asterisk just now. Okay, so as I come to the end, I want to tell you one exciting future direction. So until now, everything you saw here is, yeah, it looks cool, machine learning, but in the end, we're still doing the same core statistical method, which is we're computing likelihoods and comparing ratios of likelihoods, right? And so can we start to question the statistical method itself? One might say, oh, but Oishik, just earlier you said the Neyman-Pearson lemma is this 100-year-old lemma that guarantees that this is the theoretical best thing you can do. So how can you claim that there's anything better? What I want to say is I didn't exactly say that. I said it's the best thing to compare two hypotheses, but we never compare just two. We are always in this infinite hypotheses regime, which is called a composite hypothesis test. And in this scenario, the Neyman-Pearson lemma doesn't hold. Okay? And this was news to me. I was trained during my PhD to believe in the Neyman-Pearson lemma. So it was very fun to try to question this. But the intuition for why it doesn't hold is this. The Neyman-Pearson lemma tells us that, like this, comparing these two hypotheses, you can't do better than the likelihood ratio. But we are not comparing these two. We actually want to shrink this thing. This is the precision of your measurement, and we only want to shrink this. And there's no guarantee that this gives you the smallest confidence interval. Right? And this is not just a mathematical curiosity. I worked with some statisticians at Carnegie Mellon and we developed this thing called the focus test statistic that actually does better than the likelihood ratio. Right? So instead of just comparing with the maximum likelihood estimate, we compare any hypothesis with a composition of all alternate hypotheses. The point is that when we are doing these kind of composite hypothesis tests, we're comparing each hypothesis to everything else. And that information is encoded better in the focus test statistic. So this is the confidence interval you would get with likelihood ratio. This is for Higgs to tau analysis. And this is the confidence interval you would get with FTS. You can see that it's smaller. So you can actually beat a likelihood ratio, not just in some theoretical case, but really in a typical Higgs analysis. Now there is this f mu. If you are careful, you'll see that the integration has this weight function for every hypothesis, and that's quite important. This tells you how to focus your power. So the likelihood ratio just distributes its power across the parameter space from -infinity to infinity, right? And maybe you don't want power at 1,000 mu, right? So this focus function tells you that I want to concentrate my power near the standard model, which is where I think the value will be. And I do that at the cost of reduced power at infinity or at 1,000 and so on. Okay, so this is the sensitivity being tested at the standard model point. Let's see how it varies if I was wrong. So if I said I want concentration at standard model, but the real value is a bit far away from it. Oh, I should mention that these lines, you can see that for likelihood ratio is straight, but for this one is bendy, and you really need to use machine learning to get it. That's where the ML comes in. Okay, so we're going to look at this Higgs to tau tau analysis. This is the public data set, so it's a benchmark thing. And we're looking at how the confidence interval size looks for different true values of the parameter. So this is a universe where mu is equal to 0, this is a universe where mu is equal to 1, and so on. And we see that for a large range of them, FTS gives you a smaller confidence interval than likelihood ratio. These are already calibrated confidence intervals, so the coverage is guaranteed. What that means is a 95% confidence interval genuinely is a 95%, there's no error there. Okay, so we see that the full range, FTS does better. This depends on what focus you use. So this was a wide focus, which has like this width. You can be even more aggressive. You can narrow down your focus, and then the gain in near the standard model gets bigger, but it's at the cost of gain elsewhere, right? So because you've like bet that you want to put all your focus here, if the true value of the parameter happens to be at 4, then your confidence intervals are actually wider than likelihood ratio. Remember, this is just wider, it's not biased. It still gives you a correct confidence interval, it's just that you lose precision. Right, so here with FTS you can choose where you want precision and where you don't want precision. Okay, and with that I think I want to come to my conclusion. So hopefully I've shown you that machine learning essentially lets us remove assumptions in our methods, and so we can outperform things like the likelihood ratio test, which we thought was not possible before, and also access high dimensional data in its full complexity without having to make summaries. And similarly, we can explore these kind of high dimensional mathematical spaces for model building and try to do symbolic calculations. And I think there'll be a lot more work in this space in the future. There are weaknesses of these methods, and they tend to be the same as traditional methods, just accentuated, because the more you rely on your simulations, the more you need to make sure that the new simulations are correct and so on. But we have developed diagnostic tools to identify whenever things stop working. And yeah, so all of these methods that I talked to you about are all cross-cutting. This is the fun thing about working in AI, that you can start working on something in neutrino physics and apply it to dark matter and so on. So it's just fun, yeah, both in model building and in statistical inference. I think it's nice to be able to move from one application to another. Thank you. Yeah, so what should we use for anomaly detection? It's a good question. I don't have an answer for this, because all of this FTS and likelihood ratio, all of this makes a lot of sense when you have multiple hypotheses that you're testing, right? This is all composite hypothesis tests. Anomaly detection fundamentally is you don't have two hypotheses. You just have one hypothesis and you're trying to reject it. You're saying, I believe in the standard model, and anomaly detection has to find for me anything that deviates from the standard model. So you don't even have two hypotheses. So there none of these techniques work. So there you just treat the one hypothesis and see how, yeah, you can do anomaly detection and see how frequently you would find an anomaly if there was actually no anomaly. So yeah, a false anomaly, and then you try to make sure that you're above the false anomaly rate. Yeah, you have only the null hypothesis. Yeah. 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 Yeah, that's a very good question. Why do we use reinforcement learning? We're searching through this space. There are other search algorithms out there. The reason I'm interested in reinforcement learning is that it scales in a way that others don't. You can do like whatever MCMC, and there are many other methods that you can search, but they don't allow you to make tired decisions. So the RL agent can say, now I want to use the math package, now I want to use the physics package, or like early on it can say, okay, this seems to predict zero mass for the electron, so I don't want to do a statistical fit because zero mass is already bad enough, so let me just move on to the next thing. This kind of differentiated decision making is very valuable because we are using physics software. Each of them is expensive. It takes at least a few seconds. So we don't just want to like run every test for every hypothesis that we generate. We want to be more smart, and reinforcement learning lets you do that. Yeah. It's a good question. So, yeah, people spend a lot of time. So I should be very clear that people are very smart, and they come up with very clever ways of summaries. So there's a lot of theoretical intuition. For example, if you're measuring the Higgs mass, chances are the Higgs, like the 4-lepton mass, is a very good summary observable, because the Higgs decays to 4 leptons, and if you combine the mass of the 4 leptons, you reconstruct the mass of the Higgs, and there's good reason to think that this reconstruction will give you, this will be a very good summary if you want to measure the mass of the Higgs. So there are often, like almost always, the observable someone uses in an experiment, which is the summary, there's a very good physics reason for using it. And but people, like, this is a whole field on its own, coming up with better and better observables. There's this whole thing called optimal observables, where you're able to use the derivative, like the derivative of the likelihood, and so there's lots of statistically motivated things as well. But ultimately, they're all summaries, and in some cases, you just don't want to use summaries. Are you talking about the first part of the talk or the second? The first one. You mean where I'm building a model? Yeah. So we didn't do it for this one because the data we're using, the neutrino data, all of that assumes that the neutrino has mass. So as soon as you plug in the standard model, it just fails every test. So the standard model does very poorly in our neutrino problem. But if we did dark matter or something, well, again, it would fail to explain like gravitational lensing and things like that. But yeah, if you wanted to, your question is, I think, could we at least ensure that we recover the standard model if we give it standard model data? We can definitely do this test. I haven't done this test, but it's a good idea. We could like set standard like dark matter to 0, no gravitational lensing, or like at least no dark matter signatures, and then make sure that we're recovering the standard model. My feeling is what will happen is it'll find the standard model, but it'll also find other models that are equally good. There are so many BSM models out there that basically predict the same things. But I haven't done it, but it's a good idea. Oh, okay. That's a good comment. I haven't thought about that. That's very interesting. So unfortunately, not in the way we're doing it. So, but I'll think about this more. The reason why I'm saying it won't work for us, my agent is able to explore this space and find good models. What it doesn't guarantee to me is that it'll find every good model, right? So if this space has only 2 good models, my agent could just not find either of them, and it tells me, okay, there are no good models in this space. That doesn't, like, this is not a proof that there's some like fundamental problem. But how could you do that in a provable way? I don't know. It's a good question. That's right. At the moment, we haven't used cosmology data, but the plan is to use more. In the Zn case that I showed earlier, we gave it a whole bunch of Zn groups, and it shows which one it wants to use. And we want to extend it. So we need to characterize a whole bunch of groups so that the agent can like automatically choose this group, that group. Right now it has only a few options. We want to increase the options. But yeah, that's definitely part of the pipeline. Right. That would be super useful, I think, too. Thank you very much for being patient on a Friday evening.